If you've had exposure to basic differential calculus, I'm sure that you've seen the limit definition of a derivative. Don't worry if what I just said didn't make any sense. We're going to break it down into simple terms and see how this relates to our study of exponential functions. From this slide, just note that these are two ways to approximate the slope of a function at a given point. One is a forward difference, and the other is a central difference. Take a look at this generic exponential function, y equals b to the x. That is the curve in blue. Suppose we want to know the slope at the point x equals 0. That is shown by the red line centered at x equals 0. We call this the tangent line. How do we know what the slope of that line is? We could start by approximating it with a forward difference secant line. That is shown in green. Notice that the green line and red line are not parallel. So for h equals 2, this is not a great approximation. In theory, if we made h a lot smaller, the green line would become closer and closer to parallel with the red line. In other words, the secant line would approach the tangent line. Let's try a central difference secant line. This covers the same width as the forward difference we just saw. Except, notice this time the green line is much closer to being parallel with the red line. This is a much better approximation of the slope. That being said, I'm going to use the central difference secant line approximation in the following slides. It will give us a good estimate of the tangent line at x equals 0. So this is the rule I'm going to use. F prime of x is notation for the derivative of a function. For those unfamiliar with calculus, the derivative is the slope of a function, and the slope, given by a tangent line at a point, can be approximated by secant lines, as we just saw in the past couple slides. Slope is rise over run, delta y over delta x. F of x plus h can be thought of as y2, and f of x minus h as y1. We know the equation for slope is y2 minus y1 over x2 minus x1. Delta x in this case is 2h. This rule from our laws of exponents is going to help us out. If you'd like a refresher on the laws of exponents, please refer to a previous lesson in which I covered that topic. Otherwise, I will proceed with this one. The d over dx is just different notation for the derivative, or slope, of a function. Here I am saying that the derivative of an exponential function, b to the x, can be approximated by a central difference secant line. Letting h go to 0 is just making a more accurate approximation. In the second line, employ the law of exponents from the previous screen. In the third line, factor out b to the x. Since that isn't a function of h, we can even factor it out of the limit, as I've done in the last line. This is a summary of the last screen. It says the derivative of a function b to the x can be expressed according to the right-hand side. So what does that mean? The limit is just some constant that depends on the choice of base b. We will see shortly what this is for a couple choices of base. A useful goal is to find a base b such that this limit is equal to 1 exactly. That would imply that the derivative of such a function is equal to itself exactly. If that was not the case, then you'd have to multiply the function by some scale factor a each time you took the derivative. This isn't necessarily a problem, and it can be dealt with. However, having a scale factor of exactly 1 can greatly simplify a lot of calculations with exponentials. Let's see what happens with a base b equal to 2. In practice, I cannot actually let h go to 0, so instead, I'll just pick a number that's close to 0, like 0.1. As a fraction, 0.1 is 1 over 10, so this is taking the 10th root of 2. Look at the second line and figure out which law of exponents I used to get 1 over 2 to the 0.1. The number underlined in orange is numerically the 10th root of 2. Boxed in blue is the final answer for our limit. To get the 10th root of 2, it is possible to use Newton's method. If you don't want to do that, some calculators have a built-in function. On this one, the user would press the 4 buttons shown on the right-hand side to get the final answer of 1.071773, which has been rounded to 6 digits past the decimal. 2 y to the x 0.1 equals. There you have your answer. We could do a very similar calculation for a base of 3. Notice the final answer boxed in blue is greater than 1. With a base of 2, it was less than 1. I have plotted those two data points for bases b equals 2 and b equals 3. Then I interpolated the blue line between them. Look at the red lines. To get a scale factor a equal to 1 exactly, it looks like the base b needs to be somewhere around 2.75. Now, of course, this is all approximate. To get a closer answer, we could select bases of 2.7 and 2.8 instead of 2 and 3. This would narrow the band. We could also use 3 or 4 values of the base to apply quadratic or even cubic interpolation. We could even employ the secant method. All of these concepts are covered in my lessons on numerical methods, and I encourage you to explore those for yourself if you're curious. However, the fact remains that h is not equal to 0. You could make it 0.01, 0.001, or an even smaller number. Taking the 100th, 1000th, or an even smaller root than that is not the best approach to this, so I'm not going to waste my time showing this to you. If you do this for yourself, you will see the values approaching a limit. In fact, that limit will be very similar looking to the one we saw in the lesson on compound interest. There are ways to manipulate this expression to make that limit converge faster, and that's exactly what we're going to do in the next lessons. Before we get there, just a quick recap. If we choose a base b equal to 2, the scale factor is less than 1, somewhere around 0.7 if I remember correctly. A base b equal to 3 makes the scale factor greater than 1, about 1.1. Interpolating between these rough estimates gives us an idea of which base b would make the scale factor exactly equal to 1. That was done on the last screen. This special number we call e. An exponential function with base e will have a scale factor exactly equal to 1. This useful property makes e a popular choice among mathematicians throughout a wide variety of disciplines. So this number e is somewhere between 2 and 3. More precisely, e is somewhere close to 2.75. Stay tuned for the next lesson, in which we will compute this value a different way. Thanks for watching.